My name is Philip Judge. I am a senior scientist at NCAR in Boulder, part of the original High Altitude Observatory. High Altitude Observatory studies solar physics and terrestrial physics and the interaction. And actually it was formed, the word High Altitude Observatory comes from the High Altitude Observatory, which is in Climax, Colorado. It's no longer there, but you can find bits and bobs of it lying around. There's a big heavy metal mine up there. And it was formed by a chap called Walt Orr Roberts, who during the Second World War was charged with trying to understand dropouts in radio communications, effects on the ionosphere and stuff. And 20-odd years later, he became the first director of the new NCAR, and High Altitude Observatory was the first division of that new NCAR. So today, we're going to explore some physics of the solar chromosphere, and I'll try and convince you as to why this may be interesting and relate it to the ionosphere thermosphere system, so that for those of you who know about that. How many people here are actually consider themselves geophysicists or space physicists as opposed to solar physicists? And do we have any solar physicists at all here? Yeah, we do have a few. Okay, good. So what I'm going to do is relate it to the thermosphere ionosphere so that the people that don't know about the sun will get a little bit of orientation. First of all, does anybody want to volunteer what we're looking at here? Come along, guys. This is an easy question. Yes, young lady. Yeah. And when did that happen? This is not a fake picture. This is a real picture taken by an amateur astronomer with an amateur telescope in the line of hydrogen alpha. It's obtained during the 2004 transit, which I was lucky enough to see from England. Anybody that's been to England will know that you're lucky to see anything in the sky from England half the time, let alone a Venus transit. This summarizes to me one of the most important things about the chromosphere, and that is, this is an image of the chromosphere, and you see all these bright things, and you see these funny patterns here. It's certainly not convection. It's something different from that. Superimposed on it is a planet. And the light, not this light, but the UV light generated by the chromosphere greatly influences the planets. So this is kind of a nice metaphor for what we're talking about here. In fact, the ionosphere owes its existence to radiation from this plasma. And even better, our knowledge that there must have been UV radiation from the sun came from the 1940s, when some people called Woolley and Allen inferred that the very presence of the ionosphere itself meant that there were certain spectral lines in the spectrum of the sun. So without even knowing they were there was already predictions about this. This is a remarkable thing. The ionosphere actually was a detector of UV, the first detector of UV photons. Okay, so let's get started. And please, 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 when I use jargon that you don't understand, shout at me. I can take it. I've got 2 teenage children, and I get in trouble with those all the time. So let's have a look at the thermosphere ionosphere versus the chromosphere briefly. So this is in the chapter, whatever it is, of book 1, in which Tim Fuller-Roll and Carl Schreiber, who unfortunately can't be with us this afternoon, introduced these 2 subjects. It's mostly focused on the ionosphere thermosphere with a small section at the end, and I will expand a lot on that on this last section. So the things that occurred to me when I read through this chapter in common were these. The Earth's upper atmosphere can be characterized as a gravitationally bound, partially ionized fluid. This is true of the chromosphere. The Earth's atmosphere spans about 15 scale heights before you get up to things like magnetosphere, ionosphere, upper ionosphere, and what have you. Before you get to the corona, the chromosphere spans about 10. This is rather similar. So you've got e to the power of 10 going from what we see in the photosphere to the base of the corona. You have something called a quasi-hydrostatic balance that people use a lot in the ionosphere-thermosphere community, not in the magnetosphere. In essence, because you have subsonic vertical motions, you can infer that you've got roughly hydrostatic equilibrium. And in the in the Earth system, this number, order of magnitude-wise, about 0.1. In the chromosphere, the chromosphere is a bit more energetic. So you've got, remember that the energy density goes as velocity squared, so you've got quite a lot more power, up to 100 times the amount of power in things like acoustic waves and vibrations going on in the chromosphere than you do in the ionosphere. So the ionosphere, thermosphere region is a very quiescent place compared with this. The temperature, which is a byproduct of all the dynamics, magnetohydrodynamics, plasma physics that's going on, but I'm just listing it here as something that you should keep in mind. And generally, it increases with height because there is an external energy flux that's being imposed on both of these systems. In the case of the ionosphere and the thermosphere, all the way down into the mesosphere, it's energized by UV and EUV photons from outside. In the case of the chromosphere, we don't know what's energizing this yet, but it is, as Carl Schreiber mentioned, related to the dissipation of some kind of electromagnetic energy. So this is in common. Another thing is that you have incomplete mixing. In other words, the dynamics of and the electrodynamics of the particles it occurs on timescales at some height in the atmosphere of the Earth where the collision times become comparable to some of these dynamical times, and then elements kind of settle out. So you have different abundances. So in the exosphere of the Earth, for instance, you have a lot of hydrogen. You don't have much carbon monoxide or something, carbon dioxide, nitrogen. Same thing happens in the sun, in which case we talk about an observational thing equivalent to measuring the differential abundances of elements through the ionosphere, thermosphere. In the sun, we call it the FIP effect, the first ionization potential effect. And that just refers to the fact that if an element is ionized very easily, like lithium, magnesium, sodium, you just whack a little electron onto these things or a photon and off it bounces, it becomes charged. Those tend to have a higher measured abundance in the corona, overlying corona. And because it's correlated with the first ionization potential, the thermodynamics of the chromosphere involve neutrals and first ion stages only. That means that something's going on in the chromosphere to cause this incomplete mixing. Finally, and most importantly, the chromosphere is the place where ions become magnetized. So those of you that are familiar with the effects of cross-field conductivities and what have you in the language of thermosphere, ionosphere, we have the same stuff going on in the chromosphere, except it's going to be manifested in slightly different ways. Now, there is a class of chromospheric phenomena, very dynamic ones, called spicules, in which this number might go up to, well, the published numbers go up to about 10. You have Mach numbers of 10. That's like a 7,000 mile an hour wind at the surface of the Earth. Clearly, this is not a pressure-driven phenomenon. This is something that is related to something faster than that, and that thing that's faster is the magnetic forcing as measured through the Alfvén speed. So those are the commonalities. Now let's look at the really interesting differences, gross differences. In the thermosphere and ionosphere, unlike the higher layers of the magnetosphere, we have all this wonderful dynamics, storage of energy and all this stuff with substorms and what have you. What I gathered from reading the chapter in the book is that essentially the magnetic field is potential. In other words, any departure from a potential field, that given by the electric currents in the core of the Earth, within this atmospheric region up to a few hundred kilometers, are very small. So any electric currents that are present in the ionosphere, thermosphere, have a very little effect on the magnetic field there. And so very often what you find is that people will examine things in magnetic coordinates because the magnetic field is fixed. You just put a big old bar magnet there and you let these things move around on it. You calculate conductivities and things move around, and that's what you do. Now, if we look at the chromosphere, this is very non-potential. The fields are anchored to a photosphere, which has typical turnover times of about 8 minutes for a granule, a few hours, 20 hours or so for a supergranule. These are structures that seem to organize themselves on the surface due to subphotospheric physics. I'm going to take them as a boundary condition. In the thermosphere, what you do is you find yourself a thermodynamic state with electrons, densities, number densities of various elements and what have you. From that, you can compute your conductivity. You then have an electric field specified by some potential. The magnetic field is fixed, and then the electric currents are determined by this fixed magnetic field, the conductivity that you're given from the ionization, and this prescribed potential. This is radically different in the atmosphere of the sun. So basically, the magnetic field is decoupled here. Things move along the magnetic field, and they determine conductivities. So the transport across and parallel fields are very, very different, hence things like the equatorial electrojet and what have you. But here we've got a very different situation, because we actually have a coupled set of fluid and induction equations. Here, the induction equation, there, dB by dt is assumed to be 0. Here we have to solve for it. dB by dt is curl of V cross B. V, B. Two variables you could write as a vector. You could write density for the mass continuity equation, momentum density, that's the force balance, energy density, and then you'd have equations for the three components of the magnetic field, and an equation of state. That would close you up, for instance, a simple MHD model. And in that vector, you've got two things which are coupled, namely the velocity and the magnetic field. And those, therefore, are a nonlinear term in the induction equation, so you don't know what's going to happen ab initio. The conductivity is so high here that we have a frozen field approximation. This is not true at all at the base of the atmosphere, where there's very few charged particles around. And most importantly, while in the ionosphere J is determined under these conditions, given all these fixed things and these computations, J is determined in a totally different way in the chromosphere. It's determined by force balance. So that if I write down an expression, Newton's laws of motion, the forces, I can just add them up. J cross B, as we heard about from Amitabha, grad P again. Whatever else you want to put in here, rho G. And depending on where you are in the atmosphere of the sun, this thing is curl of H, or curl of B over mu. So this is a nonlinear term in B, with a differential in front of it. And so this, I think, tells you immediately you've got some serious difficulties here compared with this relatively straightforward case that is mostly in use in the ionospheric community. The heating mechanism is largely known. It's just you dump energy in from the sun, you take it as a given, you put in your MSIS model or you put in your EUV model, whatever you want. And it's radiative input. So you just need to know the opacity, and you need to know the source function, and you need to know all these things. Unfortunately here, all we can say is that the heating is unknown. We know it's there because it's much brighter on the outside of the sun than it is at the surface. That's a very profound thing. It doesn't obey what you'd think of as the second law of thermodynamics. I mean, if I'm cooking, chestnuts by the fire, I'm not going to get a chestnut cooked faster over here than over here by the fire. And yet that's precisely what's going on in the sun. It's getting much hotter as you go out. Now, that's a violation of the second law of thermodynamics. The second law of thermodynamics applies when you have irreversible processes, but when you have a balance between thermal, it applies to thermal processes. This is telling us only that we have non-thermal processes going on here. In other words, there's some source of mechanical energy, and it's being dissipated in situ in this plasma to raise the temperature. Another thing I found interesting was in the Earth's atmosphere, if one uses X and Y for just the surface of the Earth, say longitude and latitude and height, then generally speaking, the Earth's atmosphere is very much in the situation where the sort of orography, as you call it, the gradients around the surface are much less than the scale height of the atmosphere itself, much less than the gradients of the atmosphere itself. So this is about a 10-kilometer scale height. Yes, we have mountains here and stuff, but there's only one Everest, and it's up at 8 kilometers or something, and it's however wide. So this generally holds, and this leads to something called geostrophic balance, which geophysicists are used to thinking of. The very opposite is true in in the chromosphere, because here you have a boiling plasma underneath it with magnetic field evolving, as Dr. Schreiber showed earlier. And these are situations where, at the very least, this kind of inequality has taken place. So if you put in temperature or density here, this kind of thing is true. Okay. Why is the chromosphere interesting at all? I often ask myself this question. I've been spending 25 years of my life studying things like chromospheres, and it makes me wonder whether I'm mentally ill or not, because I don't seem to be able to get out of it. It's a difficult place to work. But there are very many reasons why this is interesting and why it's interesting right now. The things I want to draw your attention to, if you're interested in the physics of the corona, of dynamos, this is the regeneration of magnetic fields in things, in the astrophysics, space weather. If you're interested in partial ionized plasmas, if you're interested in knowing about the heliospheric UV radiation, or even the solar transition region, this funny thing that Carl Schreiber talked about. This is a gentle introduction, and I'm married to an English lit major, so I put in some references to the Tales of Mystery and Imagination by Edgar Allan Poe. So if you find yourself unable to sleep and are desperately wanting to go to sleep, this might be something you want to pull up. So it's important, as I said, because of heliospheric radiation. This shows you early on images. These are from 1980 or so, in which we see, this is observed in a line of calcium K, and we'll get into some of these things in a minute. This is jargon I'm going to use. This is singly ionized calcium. That's what the 2 means. K is Fraunhofer's original index for these lines. He just went through the spectrum and said, oh, we start with A and we go through L or something, and this happens to be K. But the reason it's important is because it shows how this is a reverse color table showing how bright the chromosphere can get when you have these things called active regions, which Dr. Schreiber described. Now, here is hydrogen Lyman alpha, and anybody who's done any physics should know that this is the most prominent line in all of astrophysics. It's the simplest transition you could imagine finding in any atom. It's an N equals 2-to-1 transition in hydrogen. And this is an early image obtained by Roger Bonnet and his colleagues, showing that there's a correlation between these things. Why is this important? Well, this radiation at 121 nanometers actually penetrates all the way down to the mesopores. And it's a huge amount of energy coming out of this thing. 10 to the minus 5 or so of the luminosity of the sun is coming out in this one line. And the fact that it's at this energy and happens to lie in a gap in the opacity, and it's generating big effects in the atmospheres of the planets as a result of this thing, gives you reason to want to study this thing. Now, these are both chromospheric. Let's have a closer look. Oh my. As Dr. Schreiber showed, we have a rather unpleasant situation here, something we really don't understand, because when I look at this, and when other people look at this, we may see different things, but when I look at this, we see lots of tiny, fine structure in there. But superimposed on it is a very large-scale structure as well. This is not all random straws. It's not like dropping a bunch of kids' straws and sticks and seeing them all lined up at random. These are oriented all together. How do you get such fine structure, but with that kind of superimposed large-scale structure on top of it? That's a question which hasn't been answered. Again, this powers the D layer in the ionosphere. And I show this in order to show you that we're still in the baby phase of understanding the basic physics of the chromosphere. If we understood this, we would have an explanation as to why it was bright along these things, why it's dark here, why they're all pointing in this direction, and not, say, randomly over here or over there or something. And we don't. What are the big questions here? What I just said. What is a fine structure? What heats the chromosphere? What drives the dynamics? Does it influence the magnetic field emerging through it? I think you can see that because it's so dense in the photosphere, and it's 10 to the 5 times less dense at the top of the chromosphere before you get to the corona, some really interesting things can happen before you get to the corona, in principle, even though it's a very thin layer. Yes, Ben? No. Coronal holes are mostly the open field regions, as Carl Schreiber pointed out. It's very, very hard to see coronal holes in chromospheric lines. It's bizarre. There's a whole lot of open questions here. That's another puzzling thing. The reason that's puzzling is because a lot of people seem to think that this comes from a lot of little low-lying loops. That doesn't make any sense to me for a variety of physical reasons. The magnetic structure of the photosphere does not seem compatible with having all these loops all over the place. These appear to me connected to very large-scale loops, and that would be consistent with the idea that it doesn't know whether the field's open or closed locally, and therefore the coronal hole chromosphere looks the same as the quiet sun chromosphere. This is taken with a Volt instrument, which is from the Naval Research Lab. These are the highest resolution images taken in the vacuum ultraviolet ever of the sun. Now, this workshop is about new opportunities and new missions. And I was asked to look at the IRIS mission here specifically. And the IRIS mission is geared up towards looking at the region where most of the non-thermal energies deposit and the temperature rise begins. This is the chromosphere. And together with the other regions, the transition region and the corona. And so let's get into a little bit. I'm going to just take a step back now and take you through what the history of the chromosphere is so I can get you rapidly up to date as to where we are. Even if you only have a passing interest in solar physics, I recommend you take a look at Young's book. Young was a professor out east, I can't remember where, and wrote this popular book. It's actually rather technical, but it's a wonderful book because it describes space weather. It's the first document that I know about that really describes this Carrington flare followed by geomagnetic interferences explicitly in some late chapter of that book, 1880 something. So if you think space weather is a new subject, think again. So this is all to do with seeing the chromosphere during an eclipse. Now I said the chromosphere is a cool thing spanning 10 scale heights. In the plasma at around 5,000 to 10,000 Kelvin, the scale height is only a couple hundred kilometers. The radius of the sun is 700,000 kilometers. 2 out of 700,000. This thing is negligible. You can just ignore it, right? Well, the reason, so it's a very, very thin thing, and it's why it's been often ignored in solar physics to do with corona, because they say, what can happen to the magnetic field in 2,000 kilometers, 10 scale heights? Well, I'll show you there's a lot of interesting stuff that can happen. But these observations refer to an eclipse where the moon exactly reveals the chromosphere in just 4 seconds. You can see the corona for 4 minutes during a 4-minute eclipse. You only ever get to see the chromosphere for about 4 seconds because the moon moves at 350 kilometers a second across the limb of the sun. And so this is some of the history going on here. The first description of it is from an English captain who was obviously confused because he was in Bern in Switzerland, which as far as I know is not in the middle of the ocean. Anyway, he described this, and this is the chromospheric flash. Young observed with a spectrograph and saw some reversal of Fraunhofer's lines. And what that means is the lines get dark in the photosphere and then they get bright again in the core, and he was the first one to see that. The very first photograph was obtained only in 33 years after the first photograph of the corona, even though it's much, much brighter, because it only lasts a few seconds. Okay. Now, this is what I think the sun, most people think that the sun looks like. In fact, there's a quote from a famous astronomer that says that if it weren't for magnetic fields, the sun would be as boring a star as most astronomers believe it to be, Leighton. And this is a sun without magnetic fields. And what do you have? Well, you have convection, turbulence, atmospheric waves. So it would kind of look a bit like this. I've smoothed it out. I mean, there would be some structure on here, but it wouldn't have any of that stuff I showed earlier. Sun would certainly have some P modes. It would have a weak stochastic chromosphere, and it had very, very minimal corona. 20 orders of magnitude less plasma at that temperature or something. I mean, you can show this. Acoustic waves basically can't do anything here, so you've got to have a magnetic field. Now, one of the greats in 20th century solar physics, observational physics, is George Ellery Hale. And even in 1903, we're used to seeing these kind of things from SDO. But in 1903, he managed to build an instrument which isolated the very, very core of that calcium line I showed you to reveal the chromosphere itself way back then. And you have to have a very high resolution, unlike the EUV imaging. But this basically reflects the interesting magnetic sun, because, as it turns out, he knew these were to do with sunspots. Indeed, you can see some here. But later on, it was found that these things are related to the magnetism coming up from the photosphere. So already in 1903, we could see that if you take a close-up look, you have this in white light. This would look like granulation. This is just boiling small granular structure that looks nothing like this. This is like a salt and pepper kind of plot where you've got a lot of noise. And then you really have a hard time seeing some of these things unless you look at very high angular resolution, which we do these days in the photosphere. Now, if we look in a line here, spectral line opacity is peaking around here. So if you look high up, if we look close to the center of the line, we're looking quite high up. It's like looking at a fog in blue light as opposed to looking through it in infrared light. So when you look at the center of the line, you're looking down only so far, whereas if you look towards the wings of the line out here, you look much deeper in. So this is basically a difference between the low chromosphere and the upper chromosphere. So he already knew that something funny is going on here. I mean, why would you ever expect this to look like this from first principles? Nobody had a clue about this. Remember, this is before the discovery of magnetism in sunspots even. And some people thought that sunspots were mountains at this point. A breakthrough came when they developed the ability to measure magnetic fields. And the pattern that you saw in the large sun is called supergranulation. And this is a typical cell here. There are cells even in active regions here like this. This is a white light picture. You just project the sun onto a piece of cardboard. This is what you'd see. This is a magnetogram. And what Leighton and colleagues found is that the chromosphere is very strongly correlated with the magnetic field, the bright chromosphere. So this explains a bit about what Carl Schreiber said early on, namely that on astronomical timescales, 10 to the 9 years, the sun changes 10 to 15%. But we now know that the sun, the sum of all this radiation coming out of these things, changes on 11 years. Where does that timescale come from? I'm not asking you to answer that question because I don't think anybody really knows. But it's a remarkable thing that given a 10 to the 6 to 10 to the 9 year time scale for internal evolution and thermal relaxation of the sun, we're sitting in this place at 1 astronomical unit being bathed by radiation varying on 11 years and much shorter than that. That is basically not explained. It's to do with the magnetic field. Okay, I presume very few of you have had stuff in radiative transfer, radiative transport. Anybody want to put that? Wow, that surprises me. Excellent, very good. Unfortunately, it's not enough for me to skip over this section. How many of you are familiar with when you look, say, at the aurora, that you're looking at a emission line, that you understand how that's formed? I mean, do you know, put your hand up if you know roughly what you're looking at when you look at, say, the red line. See, that's very similar to the corona. chromosphere is very different from that. So I've actually got to go into a little bit of detail here, and this may be a little dull, and I apologize for that, but it is important. Essential radiative transfer. So a very good colleague of mine, Rob Rutten from Holland, who's retired now, once wrote up the whole thing on radiative transfer in 100 equations. I'm going to do it in a lot less than that. And so basically, what's going on? You have a bath of photons and you have a bath of particles, and they interact. And they interact through an absorption coefficient and an emission coefficient, which I'll get to. Now, this is basically a statement of conservation of energy, such that the change in the amount of energy in a beam along a direction S is equal to, I mean, this is just the definition of the differential. So if we go from S to S plus ds, then you have a contribution. This is just saying we've got that much emission coming from this volume. That's your red or green line in the ionosphere, which when you integrate that up, that will give you the intensity. And then, but this is a trickier one. This is now saying, well, wait a minute. If I have a fog or if I have a spectral line, I can only see so far, and it's going to get absorbed out, and then it's getting re-emitted maybe in a different direction or a different frequency or something. So the transfer equation, basically, I just divide by ds, goes into this form here, and it's saying that the rate of change of the intensity of the radiation, now the intensity is a funny thing. I can give you an intuitive grasp of it, and that is that if I take a picture of the moon from the Earth, and I resolve it, in other words, I can see a disk, and then I go to the moon, and I take a picture underneath my feet, I have to use the same exposure time. That's because the intensity is constant. If the moon were far enough away so that it wasn't resolved in my camera, it would go as 1 over r to the power of 2. The intensity is a funny thing. It's the amount of power, energy transmitted per unit area, per unit solid angle, perhaps per unit frequency, perhaps even per polarization state. But the main thing is the flux is easy to understand. The amount of power coming out of the sun per unit area is easy. But the actual specific intensity is the per steradian thing is worth thinking about. So we're going to be talking about that. And here's the transfer equation written in one form. So the amount of change of specific intensity is the amount of emission along the line of sight minus the amount of absorption. Duh. And this is another form here where I've just divided J by alpha to get S. Those of you in the know that that thing's called the source function. Right. And there are places where you don't care about this so much, and there are places where you perhaps don't even, well, you always care about that one. So let's now do a formal slab. So we have a slab of plasma, and we may be at an angle cos theta here to the vertical, and that's what this thing is. And so now I've combined alpha and S into one variable called tau, which is the optical depth. This is the basic form of the simplest form of the transfer equation in canonical form, which you can manipulate. Let's have a look at this. And I want you to take one thing away from this slide. I'm just going to show you the formal solution. I mean, this is an ordinary differential equation, right? Given S here, I can just integrate this up. If I know tau and S, and I've got I at S equals 0, I just integrate this thing up. Okay. So if I know S, then I've got the solution. It's saying that, oh, I come along, and if I have some emission along the line of sight, I have to multiply by e to the minus tau over mu. This is the path length, and this is the contribution to the emission along that. This is telling me the amount of scattering. That's from the formal solution, the exponential. Okay, and actually one of the problems I've given is to do with this, problem number 2, to familiarize you with it. Now, let's do something really dirty, and those of you know about numerical quadrature might imagine this kind of looks like a Gaussian quadrature. Do you have some applied mathematicians here that recognize that kind of thing? If I can assume that I can replace this whole integral with just 1 or 2 points. Let's go the whole hog and replace the integral with 1 point. How do I do that? Let's assume the source function is the simplest form it can possibly be and still have a dependence on tau. S equals A plus B times tau. I can have a tau squared, so it's like a Taylor expansion if you like. this is very, very important for you to understand. The emergent intensity, the plus means coming out in my direction as opposed to going down the other way, is simply the source function seen at some optical depth. And if you're looking flat down on it, so you're looking flat down on it here, mu is 1. If I'm looking sideways on, I don't see quite so far down because I've got a bigger path length here. The intensity is equal to the source function at optical depth unity. Okay? That's essentially what you need to know here about radiative transfer. As you know, in thermodynamics, the relationship between the particles in a box and the radiation in the box, if it's in thermal equilibrium, you have to have detailed balance between various processes. And in that case, you can immediately write down what the source function has to be. It has to be the Planck function, the black-body Planck function. This is an example. So now, we have a prescription here. If we assume the sun is a black body, at very low frequencies, I can take this number nu to be very small. So I can basically expand that as 1 plus something small. So I get kT over h nu. So S becomes proportional to the temperature. So the radio, the brightness of the sun, is proportional to the temperature. If now I'm in the other limit, where I'm in the EUV, like Carl Schreiber was showing, I have to keep this exponential. I can ignore this. This is now e to the minus h nu over kT. The UV is exponentially dependent on the temperature of the plasma. So that's why when you look when you want to study the chromosphere and the UV and stuff, if the temperature is a little bit higher in the chromosphere, that's why you see it to be so bright, roughly because the source function is going to go to some degree with the Planck function. That's not true in general, as we'll see. Now, if I assume I have now a thermodynamic box, but I've got some photons leaking out, or if I have a box in which we have incomplete coupling between the radiation and the particles bashing around inside it, you can think of this as a coupling parameter. So if this epsilon is 1, S nu becomes B nu. It's the Planck function. It's in thermal equilibrium. On the other hand, if this is very, very small, the source function becomes something else here. What is this thing? Well, because of the transfer equation, this guy, this is the angle average of all those i's. What this says is, here I'm trying to solve for I as a function of S given tau. So if I can specify S and tau, then I've got what I need. Problem here is, I now know that this thing is the integral of I itself. So this is di by d tau equals the integral of is I nu minus the integral of I d tau plus this other parameter. We've got a integral differential equation. Here's the differential equation. The integrated part is here, where we integrate over angles. I've written that schematically as a lambda operator. This is standard notation. So this all looks very confusing, and indeed it is when you first look at it. But if you read a book like Mihalis, it's not at all clear what's going on. It wasn't for me for a very, very long time. But basically all you need to know is that now we've got a coupled integral differential equation for I. Because J is a lambda of S, S is this, blah, blah, blah. And we've got a very tricky situation here. In other words, we need to know, in order to know I, we've got to know S. And in order to know S, we've got to know I, if this epsilon is not 0. I think those of you that are familiar with some numerical techniques can see this is very, this is something that can be cast into an iterative form. So you start with a guess for S, you compute J, stick it in here, and you go along here and you solve that. Then you compute a new J. Okay. Now, the chromosphere is the place. One of the reasons the chromosphere is not very well studied is entirely because of this. In the photosphere, you can set epsilon to 1. So you have, you can put B in here, and you've got your basic solution. In the chromosphere, you're not allowed to do that. And if we go back to the analogy of the particles in a box in thermal equilibrium, as one goes up higher in the atmosphere of the sun, photons start to escape into space. After all, we can see them, right? We can see the photosphere too, but the collisions there are so strong, it's so dense, that it sets epsilon to 1. And so even if you do have loss of photons, you basically just have not an integral differential equation, but a differential equation for a given S, because you have roughly detailed balance between collisional processes. The radiative processes don't count very much in the photosphere because they're so weak. When you have detailed balance, you have thermal equilibrium. The source function in thermal equilibrium is the Planck function. Now, if we go into the chromosphere, we don't have so many scatterings. The collision, we're going down in density a lot. So the collision rates are dropping. The opacity is dropping. So photons are escaping freely into space. This is bad news because it means that we can't set the Planck source function to the Planck function. We have to solve this equation explicitly. So, in other words, what's going on is the chromosphere, before you get to the corona, where it's very thin, is becoming unable to sustain itself in thermal equilibrium. The radiation field gets out of equilibrium with the plasma. Now, the plasma itself may well have the same electron and ion and neutral temperatures. But this is saying that the photons must have a very, very different temperature, if you like. Okay, this is important because I want you to understand what Iris is going to show you. Now, the last ingredient here in these transfer things, I talked about the source function. Now I'm going to talk about the opacity, and this is related to simply the absorption coefficient times the length. So the further you go, you multiply by this guy here. This is the absorption coefficient for one height in the photosphere of the sun. And if you go to different heights, yes, the thing changes, depends on the model, but not radically. And let's see what this is. This is basically where the radiation from the sun is. So it peaks at visual wavelengths. We have our eyes evolved to see these things. And yet, here is the opacity as a function of wavelength. So as we go towards the infrared and radio, we have a high opacity. Therefore, we see not very far into the sun, so we see the outermost parts. We see the corona. As we come down here, we see deeper and deeper, and this is the place where the opacity is smallest. There's a special place in the photosphere of the sun in wavelength where you can see the very most deep things in the sun you're ever going to see. So it's like using infrared vision to see your enemy soldiers at night or through a fog or something like this. Okay? And then you have some opacity. This is all due to H minus. This is work of Chandrasekhar and people figured this one out. This is simply a hydrogen atom with an electron attached to it. Where do you think those electrons came from? Any volunteers? How can you have in the photosphere, which is mostly hydrogen, a little bit of helium, and a trace bunch of elements, how can I get an electron attached to that? Where's it come from? Pardon? No, that's a mechanism. She's a neutral bremsstrahlung. That's a mechanism for radiation at these wavelengths here and at very high energies. Where are the electrons coming from? What atoms can contribute to the electrons in the photosphere of the sun? I already gave you a clue earlier, but it's perhaps not fair. The things like sodium, calcium, magnesium are very, very easy to ionize. So the photosphere is essentially all neutral, 10 to the 5 times as many hydrogen atoms as protons, but or more than that, 10 to the 6. But there are always 10 to the minus 4 of these little things around that are ionized because of the lower ionizing potentials. Okay. That's the continuum radiation. Let's just go back here. As we come in shorter wavelengths, we get more and more opacity. This means we see what? Deeper or higher? It's more opaque. So when we look down on the sun, do we see further in, or do we only see the topmost layers? In the UV. I said you can see deepest here, so anything above this line must be higher. So these things are formed much higher up. SDO looks at this kind of wavelength here, and at shorter wavelengths here. So they're seeing stuff in the chromosphere. There is a place in here where little lines that happen to lie and have a lot of opacity can be seen in the chromosphere. This is a photospheric absorption line. We come down here and we look at this spectrum and we see, oh, it's this bright at that wavelength. What's the opacity there? Well, we know something about the opacity in the lines. This is done from atomic physics. And so you'd be able to say, well, I see, when I'm out this far, I see a long way down into the photosphere and I get this brightness. I think it's a photosphere, so it's probably a Planck function. So this is probably a Planck function, whatever the temperature is there. So this tells you the temperature as a function of height in the photosphere. And the chromosphere is this little thing in the middle. See this little wiggly S-shaped thing? That is the chromospheric emission. So you say to yourself, why do I give a damn about that? This is just silly, right? Well, it's because of what I talked about earlier. It's much hotter. If it were an LTE in equilibrium, these lines would have an enormous brightness up here. One last thing in this radiative transfer, which, congratulations for not falling asleep yet, is what happens if you really have thin conditions. This means that by the time you integrate up the absorption coefficient times length scale, it's still a tiny number. So, you just don't see anything there. Or rather, you don't see a photosphere. You don't see down to optical depth unity anymore. This is not the same thing as the Eddington-Barbier relation at all. So what we can do is, we can basically trash this term here, which was needed for the Eddington-Barbier relation. And all we have now is di by ds equals the emission coefficient. This is just a statement that the contribution along the line of sight to the intensity is just the sum of all the emission along the line of sight. This is your red and green line ionospheric case. And this is just a way of rewriting this, and this is traditionally done in solar physics. Just to orient you, I will say that it's traditional, but this is the basic equation here. So if I have that amount of emission as a function of height z at s through the Earth's atmosphere, then the amount of, say, in the oxygen airglow lines or something, then, and this is 0 because I'm looking into space, then I just know the intensity from this expression here. So I can, if I know ds, I know something about j, measured this, for instance. Same thing in the corona, with one interesting point, and that is that this thing, while it can be anything along the line of sight, happens to factor out, because of the low density limit in the corona, into a very simple function of electron temperature. And that's because you're well away from thermal equilibrium in the corona. The densities are really, really low there. Can't possibly be in thermal equilibrium. Radiation's way out of equilibrium and everything. Even the particle densities themselves, while you can still have ion equals electron equals, whatever's left of the neutral densities up there, what you have is essentially such a low density phenomenon that only 2 particle collisions count. What does that mean? I'm sitting here and I'm an ion atom, and I'm going to radiate in SDO's wavelength. Along comes an electron, bang. Oh, what do? I either excite an element, a line, in which case it can radiate, and you'll see it in SDO. Perhaps it'll recombine. But what I won't get is an electron coming in, and having, that's too rare an occurrence. The density of electrons is too small. But an electron coming in, to give, an electron going out plus another one is exactly the opposite of ionization by electrons. Detailed processing demands, for thermal equilibrium, you must have a detailed balance between 2 identical things. What that means is that if I ionize with an electron, an atom, and 2 electrons come out, then I must, if it's going to be in thermal equilibrium, have that reverse process occurring. And if that's much smaller than a competing progress, like recombination by radiative recombination or another thing, it's way out of equilibrium. So I'm just telling you that because the language of this stuff is a bit strange. But that's basically what's going on. It's all getting further and further out of equilibrium. For those of you familiar, the thermal equilibrium ionization balance is described not by the Boltzmann equation, but by the Saha equation. And the Saha-Boltzmann equation is the general formula for substates in the atoms as well. So what this shows you is, this explains now, because we only have two particle processes, electron in and electron out, and electron, the reverse processes are not balancing each other. This becomes a simple function of electron temperature. So what this shows you is the amount of ion with 9 electrons removed. X is the 10th spectrum in Roman things, so this is just the way this occurred. As a function of the temperature of the plasma, log of the temperature, you see these pick out certain things. So I mean, if you see something in SDO, in something called an ion 17 line, and somebody's done some work to identify these things, then you know it ain't coming from plasma at this temperature or less if it's close to being an ionization equilibrium, which is what these things are. If you see ion 10, it ain't coming from 7 million degree plasma. Okay? And this is relevant for SDO and IRIS because it will be observing one or two coronal lines, and the transition region lines very often form in this regime. Chromosphere doesn't, however. I don't know. There's no reason they should be. I can't remember where I got that from. Okay, so let's get to IRIS. I'm sorry, this is all probably rather academic and a bit stiff sounding, but I tried to give you the tools necessary to understand what you're looking at when you see this. So here we're looking 160 nanometers. The wavelength we look at is what? Visible. How many nanometers is that? Five. 500 maybe, 5 million? 500. This is a third of the wavelength of what we look at. This is SDO AIA-like wavelengths. This happens to be a different instrument, Hertz 9. It illustrates very nicely what you're going to be able to do with IRIS. So I'm going to change gear a bit here and get more into the chromosphere as opposed to the basic physics. So those of you that are interested in space physics and stuff can probably wake up a bit. Now, so what we're looking at here is the brightness in a continuum. And it's this one. It's right here. This is visible wavelengths here, but we're way up here, so we've got a lot of opacity here, so we're not able to see very far down into the photosphere at all. And so what you're looking at here is layers of the atmosphere about 500 or 600 kilometers, 3 or 4 scale heights up from the photosphere. And what you're looking at is the intensity at tau equals 1. And you can see it getting darker towards the limb than it is at the center. And that's because the source function is dropping with height as you come away from, just drops with height. When you look at the limb, you don't see so far down, so you're looking higher up. Therefore, you see a lower intensity because the intensity is the source function at tau equals 1. So when you look at these things with SDO, you now can say to yourself, well, I kind of understand where this is coming from now. It's coming from plasma that's like in the lower middle thermosphere, ionosphere, that's radiating out into space, and we're observing it from above. And we see that there's a lot of brightness here. So this is hotter plasma here for some reason, associated with the active region, one of the side effects of an active region. Now, in the particular case of IRIS, it's going to observe these lines here. So again, this is in angstrom, so that should be 278.0. This is about half the wavelength of visible light. And these are very opaque lines in the photosphere. You can see temperature in the photosphere is dropping to almost nothing here, and then it peaks again here. So this is the chromospheric emission, and it comes up, it peaks here. So this is a doublet line. There's another line here of singly ionized magnesium. This is doubly ionized magnesium. This guy here doesn't show any chromosphere. There is very little magnesium-1 opacity in the chromosphere, therefore it doesn't show up. This is what Fraunhofer observed, just an ordinary line that you see in the photosphere. In the chromosphere, however, you have these reversals, this very bright stuff here. So here, you have an active region, and the slit of this instrument went through here, And you can see just as it crosses the active region here, these things get very strong. And they can go up by an order of magnitude or more. So what you have is a lot of radiation coming out from the upper chromosphere, actually, in this case, as a result of magnetic activity, which is what Carol was talking about. The first problem of the set I'm giving you is probably worth one or two of you looking at. It's to identify some of the transitions here. What is this? What we've got is a spectrum of the sun obtained with an instrument on SOHO spacecraft, which was launched in '95. And what you see here, as you come along here, is happens to be a line of 1206. This is silicon 3. This line, very big one, I mentioned at the beginning, the very most strongest line in astrophysics is from what element? The most abundant hydrogen, and it's Lyman alpha, n equals 2 to 1. So here it is. It's booming out. This is a measurement of just a little piece of the quiet sun, and this thing is really kicking butt. This thing has got a heck of a lot of power in it, right? Hydrogen's very abundant. You'd think it has to be much brighter than anything else. And indeed, that's reflected here, because hydrogen is abundant in the chromosphere. In the corona, however, hydrogen's all ionized, so you can't get any of this radiation from the n equals 2 to 1 transition, because there isn't any n equals 1 stuff. It's all in protons. So that's why the corona's a really bad radiator. It's hopelessly radiating. It wants to get rid of its energy by conduction and by flows and stuff. So this thing will not arise very much at all from the corona. And then here we go along. We see a variety of other lines. These are lines of neutral oxygen, famous 1250 something, I don't know what those are. And two areas have been picked out by the IRIS team. This is where solar physics is getting pretty specialized, right? You think to yourself, well, why would you only pick those two out there? Well, there are reasons for that. And the problem number one will ask you to look into why that might be the case, for the particular case of the chromosphere. I don't want you to worry too much about these problems. They are intended to illuminate what's going on in the chromosphere. This may be very far removed from what you're used to thinking about. So, if you try them and find that it's too opaque, then we will simply step through it tomorrow. But I think it's worthwhile getting the experience of trying to identify why you believe certain lines are here and what kinds of transitions there are in certain atoms. You need to know a little tiny bit about atomic physics to appreciate what IRIS is doing in the next mission, which will be launched in January, roughly. So the first problem, we'll talk about why those as opposed to these, whatever. So I deliberately have not shown you, these are the two windows blown up of those two things I showed you. So here's 1, 2, 1, and 2. Quiet sun. And here's it blown up. And in here as well. And one of your tasks will be to identify what you think these things might be. And you'll have to use your wonderful skills on the internet, probably, to find those. Clues are in some of the names I've given you. There was a Hertz experiment done. You might want to look at that. Sumer, whatever. Interestingly enough, here's an old buddy, Alpha Centauri. And this has very similar spectrum to the sun, and with actually a higher resolution and a higher signal to noise. How can that possibly be? Alpha Centauri's first magnitude, logarithmic scale. The sun is minus 27. Well, they're after different things. One's taken with the Hubble Space Telescope, the other one with a solar instrument. Okay. Let's speed up a bit. Why must chromospheres exist at all? Well, if you think about it, the photosphere is at some pressure of, 10 to the 0 in dynes per square centimeter or something like this, and the corona's at 10 to the minus 5, well, you can't go from one to the other, or otherwise the thing will blow off, right? I mean, pressure gradient's a force in the momentum equation, so photosphere will blow off. So there's something in between, even though it's often ignored. For any reasonable heating mechanism, the sun must produce a partially ionized stratified upper atmosphere in the same way that thermosphere ionosphere is driven. This is roughly what's going on. This is the amount of heating per cubic centimeter that you need. This is an energy flux in per square centimeter. And this is the canonical number here, the number of ergs to maintain the chromosphere at all. And if you have it roughly subsonic, and you have an energy balance situation, it's going to have to be partially ionized. Well, why is that? Let's look at the energy equation, because we're talking about ionization, temperatures, and they depend on these things as well. Here's the internal energy of a particle of fluid given the gas pressure, and here's the ionization energy. This number is about 20 times the thermal energy, that ionization hydrogen. Very, very important. So you're in a state where you're in a plasma where the ionization energy is much, much higher than the mean speed of the electrons, say, the mean energy of the electrons, as shown here. Here's the equation of state. Here's the energy equation. This says the rate of change of internal energy, right? And we're going to get through here. There's the temperature appears through the equation of state there and the densities. And so rate of change of the internal energy of this plasma is given by the divergence of the enthalpy flux, standard form, and whatever heating we put in, and then I put in a radiation loss term here. The radiation losses tend to go in this kind of form here, because if you have a threshold T0 in your atoms that are radiating, by the time it gets ionized, the Boltzmann equation, the Boltzmann distribution of electrons, tells you that the number of electrons available to knock an atom into an excited state with an equivalent energy of T0 is this. So, in fact, the radiation loss is actually very exponentially, very nicely like this when you average over all the atoms. And then, furthermore, the ionization happens to go in something like in this way as well, because, again, for the same reasons. This is an energy loss. This is a removal of electrons from hydrogen. And if you piece these together and think about it, I'd like you to do that, what you'll find is that the chromosphere is an incredibly good thermostat. I can dump massive amounts of energy in here, and what I'm going to end up doing is I'm going to increase, instead of increasing the temperature very much, I'm going to increase the number density of electrons quite a bit, but then temperature can't go up very much. It only requires a very small amount of temperature to do that. In the meantime, it's then radiating a lot as well. So there are two reasons why the chromosphere must exist. There seems to be a source of mechanical energy. The sink of internal energy in terms of ionization is huge, so I pump energy into this thing like crazy, and all I'm doing is moving more and more electrons from the hydrogen. And also, the radiative losses are also increasing exponentially with temperature. I've got a perfect thermostat almost. So the chromosphere must exist. And this is what it looks like in stratification. And when you look at those figures, you'll say, this is 2 megameters long. Those things I showed you in trace were, or in the images with Lyman alpha, were maybe 15 megameters long. What the heck's going on? Well, you have to be a bit careful here. This is a tricky area. What's going on is that you can send stuff up, and it's cooling off much higher up. So this is the photosphere, chromosphere. Corona is supposed to start up here. And this is 2 megameters above the photosphere. And this again, this is what EUV lines, this is the spectrum that SDO was looking at, that thing I showed you with the limb darkening. Here are the infrared and radio observations. So this maps to opacity. This is very high opacity, very long wavelengths, 3 millimeters, 1 millimeter. So you're looking deeper and deeper in the atmosphere until you get to 1.6 microns, what you see down here somewhere. And then you come up in the UV and you see higher up again. And this is where Lyman alpha is formed at the very top here. The magnesium line I showed you is formed up here. I would argue that, and some people I don't think quite appreciate this, that no matter what you do with the Lorentz force here, you can't avoid the fact that grad P and rho G sort of have to be in balance if you've got subsonic motions. And unless you've got bubbles of plasma continually coming up driven by the Lorentz force, which you don't have, this stratification has to be sound. So even though you see wonderful things sticking out of the sun in the chromosphere, you actually are looking at the tail of distribution, and you've basically got an exponential brick wall of material that you're going down that you can't get around. So it's just an extension of the atmosphere of the photosphere. If there were no heating, it would just continue to do this, the temperature, to an radiative equilibrium temperature of 4,000 K or something. Okay. Now comes the gee whiz stuff, which is that's the elementary stuff. The gee whiz stuff is about what are we really looking at when we look at the chromosphere? Well, let's take a really good close-up look here. This is a granule. This is 1 megameter across, right? This is 1,000 kilometers. This is about the size of Texas, like Harold was saying. These things are tiny. You know, these things are about the size of a Boulder County or something. No, not that small, but fairly small. What are we looking at? We're looking at the photosphere of the sun, and we're looking at something which, when you poke a hole in the photosphere, radiation comes in and radiates out from deeper down, and we know that the photosphere gets hotter as you go down, so the radiation is brighter down there. So what we've done is like poking a straw down and looking into the deeper part of the atmosphere of the sun, and you see that it gets brighter. So these are magnetic elements, and you can see that because here's a magnetogram, and you can see a correlation between the magnetic field and these things. Okay? All right. This is now a chromospheric image, but it's very, very broad. Remember I showed you right at the very core of the calcium lines, it's about 1 angstrom wide, 0.1 nanometers wide at the core. But now this is an observation with 3 of those, or 3 times wider. So we're looking at a mixture of the photosphere and the chromosphere. If you ever get involved with chromospheric physics, you really have to pay attention to the band passes people are using. You will see something totally different if you look with a very high, much narrower band pass. It will not look anything like that. Okay? And what that means is that the opacity is changing so much through as you go to line center, that you see stuff that's maybe 4 orders of magnitude lower density suddenly than you were looking at when you look at this thing. Okay, and here's some stuff I'm not interested in at this point, to do with granular dynamics. But this is basically showing us what we've got underneath the chromosphere, and this is what the chromosphere, or the low chromosphere, would look like. That's what this is showing. Now, just to remind us, this is sort of out of order a little bit. I should have put it earlier. In the interior of the sun, one has not a force-free state. So you have J cross B and grad P and rho G and, you know, viscous and whatever forces. And J can be absolutely anything. And this is a cartoon from Thomas Gold, 1964, very famous, somewhat controversial guy, but very provocative thinker for the time. And the stratification makes this very thin, and so many solar physicists tend to think of it exactly like this. It's just a black line. But in fact, you're going through 4 orders of magnitude in pressure going from here to there before you get to this force-free corona. That's just to reinforce what I was saying earlier. I think you can see that this system going from J equals anything to J cross B equals 0, this means that any currents must be parallel, therefore they wrap around the magnetic field lines. This is going to have some interesting things going on with it. So what does this thing look like in time then? I mean, this is a real clock going here. You look down on the chromosphere, you see funny stuff going on. This is the core of the line, so we're looking quite high up. This is a very quiet region of the sun, actually. And yet you can see there's a lot going on all the time. These things in here are little patches. This is in arc seconds, so actually it's arc seconds, I think. So what you can see is these funny looking flows and stuff. And this is dynamics going on a time scale of a few minutes. These things go on in a couple of minutes. This stuff kind of averages out to be the same all over the sun. This stuff depends on the magnetic fields. And this is a very, very quiet region. So what IRIS will be doing is looking at these things in greater detail. And the interesting thing will be mostly this stuff. The physics of this part of the atmosphere is sort of understood now in terms of propagating disturbances that are left over in the photosphere coming up into the chromosphere. This stuff is not understood at all. Now, I used to have a lot more hair on top of my head, and it looked more like this sometimes. And it's what we're looking at here is the limb of the sun. This is to illustrate a point that some solar physicists, I don't think, quite appreciate. So with the Hinode spacecraft, you can observe a broad thing of an angstrom or so wide in calcium, and this is what this is showing. And this is a movie, and I apologize, I don't have the time scale on here, but you can sort of see what it is, because this is oscillating at a 5-minute period here. So this is maybe 20, 30 minutes worth of data, or maybe a bit longer than that. But what they found was, when you look at the limb, you see all this stuff sticking up into the corona, and yet we know the chromosphere is just this thick. How on earth can, what's this got to do? If this is the chromosphere, where's it gone? Turns out that that's because of the bandpass problem I was talking about. If you would look at the corolla line, this would be full of material going up and down everywhere, and you would see a very thick layer of a chromosphere sitting there. Whereas this thing picks out stuff above the limb, and actually it's been enhanced to show this stuff above the limb. So when you look at this stuff, you've got to be very careful. This is something that IRIS will be focusing on in great detail. Dynamics. I was asked to talk about dynamics. You look down on something, these are granules again, about the size of Texas, okay? And these things called, they call them type 2 spicules, and they're called blue shifted events here. What they are is, here's the lower chromosphere. Here's a little bit mixture of upper chromosphere rapidly moving. So here is the line wing, far away. This is getting closer to the line core. And in this particular line of hydrogen, 2 to 3 level, not 1 to 2, it picks out photospheric features like these granules, and it picks out stuff moving very fast. So in other words, if I normally look here, I look down on the sun, I see straight down into the photosphere at this point. But now, if I look through this thing here, and I look at the profile, it turns out that it has a blue shift. So the whole line has been moved, so suddenly what I thought was thin is now thick because I've moved the whole line over, and I've got this big old opacity thing there. So this thing is now a combination of photosphere, which is very nice because you know where the granules are, and now you can see where this high velocity stuff is. And this is yet another realization of that, different velocities. Now, what does this mean? This is now plotted on a Doppler scale. Look at this, 70 kilometers a second. That's a Mach number of about 10. Something serious is going on here. And look at the shape of this thing. This is turbulence. This is not turbulence, this is a jet. This is highly ordered. Something in the chromosphere is going on to make these things want to become these long, thin things like this. As I pointed out at the beginning, this fine structure is not really understood. Reconnection is certainly part of the story here. But reconnection in the chromosphere is going to be different from what you've been thinking about in the idealized cases. Most obviously because this chromosphere is stratified. If I've got a magnetic field in your sweet Parker layer, which Professor Bhattacharjee talked about, and I recombine it, and I take this component, and I reconnect it, and I recombine it, reconnect it so that you get jets coming out like this. The upward-going jet goes up into the corona. There's no mass there. There's no inertia there. It just keeps going. That's what you're seeing here, most likely. On the other hand, the bit that's going down runs into this brick wall. It's only got to go 100 kilometers, and it's gone up by a factor of E in pressure. That means that you're going to get a rebound. So the reconnection in the chromosphere should have a very different observational signature from other places in the atmosphere of the sun. And it does. The Hinode spacecraft has shown fairly odd-looking anemone kind of jets that are quite asymmetric. But they're not fully understood in terms of the dynamics of these things like this. So this is my explanation as to why you only see these blue-shifted things here and not very much red-shifted, which you do see in the lower density plasmas of the corona when you have reconnection. Okay, one of the questions for IRIS is what role do the Alfvénic waves play? This is this movie again, and again, I actually have a time on this one. There is a small army of people working on these things and on these things. And again, you've got to keep in mind, this is a very much filter-dependent image. If you observe it much higher resolution than I showed you earlier, then you would see a very different kind of phenomenon here. But look at this remarkable dynamics, all this stuff going on. This is cool plasma sticking up into the corona where it has no business being. And this must be due to a force operating in the chromosphere itself lower down, be it a Lorentz force as a result of things like reconnection, or be it something else, like a ponderomotive force due to waves. We don't really know yet. But this also shows you one other thing, the transition from the higher beta plasma to the lower beta plasma. Look at the disorder in here. I look at this and I see a mess. I see a bunch of waves propagating. I see, granules. I see, upflows, downflows. It's just turbulence in some sense. This is not turbulence. If that's turbulence, where is the motion in this direction that's counteracting the motion along this direction? There's a very definite order to this part of the atmosphere, and this is because J cross B has very little to compete with it. And turbulence in a low beta plasma looks very, very different from a high beta plasma, which is underneath the surface. So the IRIS mission is designed to look at this stuff, and we want to find out what's left for the corona. And one way to do that is to look at these things as traces. This is like looking at lights on the Christmas tree, and the wind's blowing the Christmas tree, and it's waving to and fro. You can't see the tree, but you can see the lights on it. And these things measure the amount of stress in the boughs of the tree, and you can tell what kind of oscillation modes you've got. And you can then calculate, if you assume a certain thing about the phase relationships of the waves and what have you, what the energy going into the atmosphere is. Turns out there's enough energy in these to drive the solar wind in coronal holes. Perhaps not surprising, because it's hard to imagine what else there would be, but that's an observational fact now. What might IRIS actually see? And, well, these are older data, because I like going back in the literature. Ken Deere and et al., there was this beautiful experiment called Hertz from the Naval Research Laboratory, which went up on several rockets and even flew on Space Lab. And it might be that the International Space Station might want to do something similar again at some point. Who knows? But anyway, what it did was it observes with a slit jaw. So you project an image of the sun onto a spectrograph slit. You take a photograph of the slit jaw. That tells you what you're looking at. And then behind that, the light comes through the spectrograph and gets dispersed. And you see the spectra shown here. And that's what these are. So this is just a little line. It happens to be of carbon-1 at 1561 angstrom. It could be, whatever you want. So IRIS might see some of these things here. And what I'm interested in noting is that this was the highest resolution images. These are half-arc second pixels. These are very comparable to what IRIS will do, only this is photography, not CCDs. So what's intriguing to me, that even at this very high angular resolution, this is a Doppler shift as seen as you go along the slit. This is the Doppler shift measured in these lines. And you can see this thing here, it's moved out a little bit sideways, and then here again. So this is these are 10 kilometers a second. These are subsonic speeds. Where are these huge speeds that we're seeing in hydrogen from the ground? I don't know. They should be here, and they're not. So I'm encouraging you, if you're interested, to get involved with the IRIS mission, because it will make some discoveries here. It's a much better instrument than this, in the sense of having a much better detector. I can't explain why this is a factor of 10 less than what we see in the optical lines. And there's something interesting going on. The optical lines show pure absorption. These are emission. If anything, I would expect that the emission lines would reflect faster dynamics better because you've got a lot more energy involved. So in any way I look at it, I can't reconcile why we don't see these things. I think IRIS is going to make some surprising discoveries here. Here is the same thing for some transition region lines. What you see here is very large excursions. Here's the limb, so you see stuff sticking above the solar limb. Here's the disk of the sun, this center here. These are infamous lines of 3 times ionized carbon, which are very easy to see. See these dynamics here? This is associated with active regions and sunspots. The rest of the time, it's relatively quiescent. So the point here is just to show you that in the sun, a big deal is made out of a lot of dynamics. But when you look for dynamics, that's what you're going to find. It's like, you know, if you're a bird watcher and you want to go and find the lesser spotted, you know, small-breasted cuckoo, that's what you're going to find. You don't care about the fact that there are 10 to the 12 blackbirds flying around. You only want to see these cuckoos, and so those are the ones you're looking for. I'm not accusing the solar physics community of just doing that, but what I am saying is you have to be exercise a little bit of judgment in assessing what the status of chromospheric physics is in this regard. Because, if I go back to here, for instance, your eye is very much attracted to this stuff, and you don't give a damn about that. This is a new discovery. We've known about this stuff for a long time. The fact that you're missing most of the chromosphere here because of this bandpass wasn't recognized. So, those of you that are interested in that kind of thing. So here again is a summary of what was learned from Hertz, which again is rather comparable, not as good. The significant thing I want to point out are these things here. These are rather different now from what people have been talking about in these new high-resolution observations that they want to test with those numerical models. And yet the conditions in which they're formed are very similar. Something's not quite right here. Okay, I'm going to finish up with a contradiction. The one thing I decided to avoid in this discussion was anything to do with real dynamics, numerical simulations of waves, of reconnection, and what have you, because you get enough of that with this stuff in the magnetosphere and what have you. And that's a weakness of what I'm doing here. But there are some interesting results out there, and I'm just going to point out a couple. The magnetic field, as I showed you, the chromospheric emission expands with height. The magnetic field must also do the same. And one of the problems, problem number 4, talks about you'll try and figure out where the plasma beta surface is 1, what it looks like, and this kind of stuff. When you have an inhomogeneous field, it's pinched at the surface by something in the photosphere, and then it expands out. And you've got a stratification of the atmosphere, and then you've got the overlying corona. Under those conditions, if I were to draw a surface of constant alphane speed, it could look almost like anything. I mean, it's going to be somewhere, but it's going to go up and down quite a lot. And if I plot for a given alphane speed, and if I plot it where it equals the sound speed, for instance, you know, that's going to be a specific surface. Now, if I send up a sound wave, or if I send up an alphane wave along field lines, something interesting is going to happen when those phase speeds are the same. It's called mode coupling, and you can expect some rather dramatic things to happen here. One of the results that came out from a simple calculation by Paul Calley recently is that he believes that active region chromospheres are alphane wave factories. This is very interesting because what it's saying is it converts, you take an ordered motion like a sound wave or some kind of buffeting due to granular motions, and you convert it into an alphane wave in the chromosphere. That depends on, the efficiency of that depends on the temperature, on the magnetic field, etc. In other words, it depends explicitly on chromospheric physics. That means I can't take the photosphere and go straight to the corona and expect to get anything sensible out of it. If this is correct, this is a major and interesting thing. And the basic idea here is that the chromosphere is a mess, and if you take idealized models, you tend to select out certain kinds of solutions that are perhaps singular, or not singular, but are not general enough. And when you relax certain geometries, such as here, you get new phenomena that occur, and these must be happening in the chromosphere. There's no way that a wave vector of a sound wave and a magnetic field and gravity are going to all accidentally line up all the time on the sun. In fact, that's very unlikely to happen. So these things, we have to take them seriously. And so chromospheric dynamics is a very rich area, and I think Iris is going to show us a lot of stuff. Now, just to finish, a couple of things. Many of you will be familiar with the Pedersen conductivity, which I call Cowling conductivity, because I'm English. And one of the last problems talks about the essence of transport in a multi-fluid plasma like the chromosphere. And it talks about pressure gradients entering into the dissipation rates, into the Ohm's laws. Basically, the equations of motions of the ions, neutral, and electrons can be combined into a form which I like very much by Buginsky in 1965. And they have various names, these effects here. But one of the things that happens is that you can end up with an enormous amount more dissipation and cross-field effects owing to ion-neutral friction if you can generate motions across the field to drag the neutrals through the ions. You can end up doing a lot of heating, and this is very promising for the heating of the chromosphere. Not at all proven because it's a very model-dependent kind of thing to be able to model this. But if you have any cross-field dissipation whatsoever, any cross-field current whatsoever, the likelihood is it's going to get dissipated very rapidly, because this is the gyro frequency times the collision time. This is the number of times it goes around before it collides, and that's the same for the electrons. These are huge numbers, and so you can dissipate a lot of things. This means that the chromosphere is a filter of cross-field currents, in principle. It takes away cross-field currents. What does that mean? It makes the currents more parallel. Well, the same thing is going on in the force balance, because as we go from the photosphere, where we have J cross B is not equal to 0, it's trying to get to be parallel, J cross B is equal to 0, in the corona. This has got the same effect. So the chromosphere is an active role in changing the magnetic structure in the corona. To show you that, I've just one result. This is just the magnitude of the perpendicular current computed by these guys as a function of height index up there in the atmosphere, given with a fully, where you switch on or off the Pedersen dissipation, this cross-field dissipation. And this is the cross-field current you get for a fully ionized plasma, and this is the cross-field current you get. These differ by an order of magnitude, at least. So this is not a small thing here, and in fact, Alfvénic fluctuations should be damped out by this. So that's kind of contrary to Paul Cali. What I'm trying to tell you is that this is a rich, open area for research. We need better observations. IRIS is one way to do it. So here's IRIS. It's going to observe this stuff. The models are part of the IRIS mission, actually, the radiation MHD models. These are models in which you have to solve for a full vector, state vector, which not only includes density, momentum density, energy, and then magnetic field in an equation of state, but you replace the equation of state with a whole bunch of non-LTE equations for the populations of hydrogen, helium, you name it. And then you self-consistently compute everything in one big go. This is a major calculation, major big calculations here, very difficult to do. The group in Oslo has done this, and they're probably the world experts on this. Anybody interested in this at all should definitely contact them. So they're in the business of trying to model all this stuff, Here are the magnesium lines again. So here's the characteristics of the thing. This is a 20-centimeter telescope. The telescope's this big. How can you do solar physics with a telescope this small when people want to build 30-meter telescopes? Well, the sun's bright, I guess. Okay, and one of the things is that I haven't mentioned is that what you really want to get at, the energy is in the magnetic field. When you observe with iris, you're observing the plasma with no information essentially on the magnetic field, only indirectly. And there are instruments around that can do that. Anybody interested is welcome to talk to me or whatever. What you want to do is split up the light into its polarization states. Here is the facility in Sacramento Peak, beautiful observatory. It's going to be closing down in a few years to move to Hawaii with a new big telescope. This is a 1960s telescope. This is an infrared spectrometer. In particular, it observes helium. Helium being the solar element, right? So it's what you can do is you can attempt to get at, instead of just intensity images. These are very noisy because these things are 10 to the minus 3, 10 to the minus 2, 10 to the minus 3 of the intensities of the things I've shown you before. So if I measure the intensity of a line, I've got to do 100 times better to detect this at all. And what I want to show you here is, I don't expect anybody to understand this that's not familiar with it, but this is showing you information. This is the Stokes profile showing the strength of the magnetic field, proportional to the strength of the magnetic field. And here is an image showing an active region in which we've finally detected plumes of plasma going into the corona. Here we can measure the magnetic field in the corona for more or less the first time in this technique. And that's something that we want to do to augment the IRIS mission. And I'll stop. Statistically speaking, yeah, there's a curious thing. So the question is, when you look at atoms that have a few electrons removed from them, they tend to form in between the very hot corona and the chromosphere, which is at 10,000 or less degrees. And they're formed in fully ionized plasma. And the thing is, the question is, we see, when we look at the sun, you see that the lines appear to be red-shifted. In other words, if you were to interpret it straightforwardly, you'd say the sun is gaining mass because you've got downflowing plasma everywhere in these particular lines. Well, this is not the case. The sun is not gaining mass. It's losing mass. So how can this be? Well, the atmosphere is very inhomogeneous, and what you see as bright in one line is not the same thing as a mass flux. A mass flux is rho times V, whereas what you see as bright in a line is actually electron density squared times some function of temperature. So it's a very, very different thing. Now, the problem with the chromosphere is this very resilient, robust thing, which no matter how much heating you put into it, it's going to try and maintain itself, and you're going to burn down the corona a little bit. And all the energy is going to go into ionization and radiation, and it's really not going to change the temperature very much. In between the chromosphere and the corona, 1 million and 10 to the 4 degrees, is an interface region. And that interface region is very, very steeply structured because of the dominance of electron heat conduction in the upper parts, and for some reason we don't know about the lower part, the energy balance. But it means it's very thin. There's almost no mass there. So when you look at lines formed between 10 to the 4 and 10 to the 6 Kelvin, remember I showed you those ionization plots and said the ionization. And Dana pointed out that one of these is at carbon-4, is right smack in the middle of the ultraviolet spectrum. These things form in this very tenuous plasma. This is a tail with 2 dogs. I mean, the dog there's a lot of energy in the corona that's coming down by heat conduction, and if the corona is inhomogeneous, it's going to create things in the transition region which are going to be more inhomogeneous, owing to a nonlinear dependence of the energy flux on temperature and what have you. And then from below, so you've got a dog above waggling the amount of energy going into the transition region, and then you've got one from beneath, because if you heat the chromosphere enough, it will get up to those transition region temperatures eventually. And so there are two different mechanisms by which this thing can radiate, and it's not surprising that it gives you very interesting results like the one that Dana just pointed out. My personal view is I worked on the transition region a lot when I was younger and gave up because I didn't know how the hell to handle it. To me, it seemed like a tail with two dogs to it, and I didn't want to study that. I wanted to study the dogs. I want to know where the energy is that's driving this thing. Now, it's been very popular in space physics, and it's a quirk of nature that the grating spectrographs that people have used, for instance, at Naval Research Lab, from about 1150 angstroms and up, from Skylab onwards, we had a lot of data in this region, right? 115 nanometers on up. And those are normal incidence gratings. Below that, the UV photons sort of go straight through the coatings. So when you look above that wavelength, it just so happens that many of the lines are chromospheric, but you get a bunch of them in the transition region as well. And so hundreds and hundreds of papers have been written on the transition region because it does all kinds of stuff. Well, the dog's tail is whipping around all over the place, so therefore it's going to do a lot of stuff. I personally am a little dissatisfied with those studies because it seems to me to be a study of something that's blowing around in the wind as opposed to the wind itself. So I would encourage you to study the chromosphere and perhaps even the corona at this point. It sounds odd to say you should do it, but it's because of the energy flux coming down that it's important, the corona. There's a student. I think I think they're more randomly driven. I think it's likely to be something that's I would have to check, but my understanding of these simulations that this group does, I mean, these are enormous calculations. I mean, they take ages to run. Three-dimensional radiation magnetohydrodynamic non-LTE calculations. God, it makes me feel ill even to say that. And then, I mean, you can imagine knocking something. It's gonna want to relax at a certain frequency. And so if you see something that's periodic, it may be because of that. There could be other reasons as well. For instance, they have, of course, you know, you're working in a Lundquist number which is very low in comparison with the sun. So, for instance, you might end up getting to a point where you do a lot of reconnection, and then it settles down. And you do a lot of more reconnection. So you may end up with a quasi-periodic thing because of that. I really don't know, though. Yeah. You would think they would be, but the dynamics that you see here is much more stochastic than that. It's more like the substorm kind of regime you were hearing about, where you store energy and then release it. And in these models, you can't store a lot because the Lundquist number is not that high, but it's high enough to do that. And I think a lot of the dynamics comes from that kind of process. Yeah. 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 I don't know if we know enough about the chromosphere. I mean, the chromosphere is a robust thing in itself, but there's no one model of the chromosphere that means anything in some regard. So you wouldn't be able to separate in height, say, where a certain kind of dissipation is going on or not, or a certain kind of Ohm's law. I have not looked at Hall effects because I'm mostly interested in the heating problem, so it's not relevant because Hall is not dissipative. But that's just my bias. I do know that the Pedersen, depending on the motions you put in, the Pedersen or Cowling conductivities, that kind of dissipation, it has to be going on. You can't avoid it. But whether it's a dominant thing in producing what Hale and everybody else has seen since in the chromosphere in terms of thermal structure is, I don't know. Because we don't know what the basic motions are and how much energy there is in those. If we were to measure we have some constraints on it because we know how fast the chromosphere is moving and stuff, but we don't know things like magnetic field strength very well, density very well, so we don't know the propagation speed of alphane waves very well. We don't know what the energy flux density is, and therefore we can't tell what the heating rate is. Oh, so at the very beginning I talked about the fact that J is determined by the force balance in MHD in the sun's atmosphere. There is some confusion that has arisen. Where are we? So the question is, I'll just talk. The question is, in the ionosphere and thermosphere, you have this given magnetic structure and you have certain thermodynamic situation, and then you can solve for the electrodynamics given this set of equations. In the chromosphere, it's not like that at all because you have, yes, you can compute your conductivities. They're the same formula, you use the same things. They may well have pressure gradient terms in them that you don't have in the ionosphere because it's significant. But the real essence here is that J is not determined by anything to do with the electrodynamics. J is a consequence of the Lorentz force being out of balance or in balance with other things in the MHD approximation. And whether you include cross-field conduction or not, the neglect of the displacement current in MHD gives you an instantaneous solution to the equations in which J has to satisfy the force balance. And what happens there is J is going to find its way no matter what, because the dominant driving term in the equations of motion is the force balance and not, given the structure, the J equals sigma E kind of conditions. So you can't think of the chromosphere as I don't think it's useful to think of the chromosphere in terms of electric currents. There's been sort of a philosophical debate about this. I mean, you have Gene Parker on one hand talking about MHD being a V and B paradigm. In other words, you have to solve for the momentum density and the magnetic density. And then you have the J and E paradigm, which is in space physics and in particular in the ionosphere, thermosphere. The chromosphere is one where you really have to acknowledge that the system is driven by, very strongly driven by pressure gradient forces, by Lorentz forces, by other things, and therefore the current just has to adjust itself to satisfy that, and then the conductivities or whatever have to take care of themselves, I think.